Hello, I'm back with part 2 of lecture 21. So in the first part, we defined the Laplace transform to be a Laplace transform of a function f of the variable t is the function of the variable s defined to be the improper integral from 0 to infinity of e to the minus st times f of t dt. And last time we figured out the Laplace transform of the constant function 1 to be the function 1 over s defined for s greater than 0. Now, before I continue with other examples, I want to give you a general theorem. I'm not going to prove it, but we need something like this before we continue. Which type of functions have Laplace transforms? Because the Laplace transform is defined in terms of an improper integral, so for the Laplace transform to be defined, this improper integral should be convergent. So the, of course, it's going to be convergent for some values of s. Okay, so what kind of functions have this property? So suppose f of t is piecewise continuous. On the interval 0 infinity, so that we have the Laplace transform defined. And also suppose that there are constants constant k and constant a. These are real numbers. Such that absolute value of your function, for the convergence of the improper integral, we are going to use a comparison theorem. And for the comparison theorem, remember, the absolute value of the function should be less than some function whose improper integral converges. So we take absolute value of our function to be less than or equal to some constant k times the exponential function e to the at for all t greater than or equal to 0, because this is the interval we are looking at. Then the Laplace transform of the function exists. So that means the improper integral converges for s greater than this number a. You see, the improper integral is going to be convergent for some values of s and divergent for some other values. Okay, the proof is basically the comparison. Proof depends on comparison theorem. So instead of the function f, we are going to use k times e to the at. So if you look at this improper integral, e to the minus st, and instead of f, if I use the function e to the at, this is going to be k is constant, limit m goes to infinity, integral from 0 to m, e to the power a minus s times t. So this is going to be, the integral is with respect to t. So 1 over a minus s times e to the a minus s t. So s is not equal to a. Okay, from 0 to t, from 0 to m. So this is similar to the example we did last time when we were trying to figure out the Laplace transform of 1. So we have limit as m goes to infinity, 1 over a minus s, e to the a minus s times m minus 1. So again, this exponential piece is going to the limit as m goes to infinity is going to be 0 when the coefficient of m is negative, meaning when s is larger than a. So this limit is going to be k over s minus a if s is larger than a. So when s is greater than a, this function is convergent. This improper integral converges. So by comparison, then the improper integral of f also converges. So that's where this condition s greater than a comes from, so that the limit of this exponential exists. Okay, now, so this is basically the sketch of the proof. Now, before we continue with examples, I want to give you some remarks about the implications. By the way, okay, this theorem, this condition, okay, basically in our examples, we are going to evaluate the integral to see that it exists. In general, if you need this condition if you're going to say anything theoretical, anything in general, for general functions. And this condition, okay, so this is like saying that our function, at least in absolute value, is not any faster than the exponential function, okay? Remember, in calculus, we looked at the limits to compare how fast a function goes to infinity. We know that the exponential function is faster than any power function. So basically, this is going to be the case, this condition is going to be the case for any function involving a power of the function t. So polynomials, rational functions, functions involving radicals, sine and cosine also, but this is not going to be, so exponential function is faster than any power function, but if you take a function exponential of the exponential function, something like that, it's not going to satisfy this condition. So that's my first remark. For some functions, it is not possible to find such constants k and a. For example, e to the t. So twice exponential, it is faster than the exponential. It's the other way around. So, so for this function, the Laplace transform of this function does not exist. For any value of s. Okay. Again, when you consider the proof, the comparison theorem, the values of s for which the integral converges, for which a Laplace transform exists or converges, for any function, is of the form either S greater than A or the empty set or all of R. Okay. So the integral may be convergent for all values of S. I guess this will be the case, say, a constant 0, for example. So the Laplace transform is going to be 0 for every S. In general, in our examples, we are going to get an interval in the form S greater than A. But as you see in the first remark, empty set is also possible. Something like e to the t doesn't have a Laplace transform for any value. Now the third one, it may look confusing, but it is convenient to consider the variable S instead of a real number. It is convenient to consider our variable S as a complex number. So S is a complex number in the form x plus iy, where x and y are real numbers. So in this case, the condition that S greater than A, because for complex numbers, this doesn't make sense. A complex number cannot be greater than any number, becomes real part of the number S greater than A. So if S is x plus iy, real part is the number x. So we consider complex numbers. So if you consider complex numbers as the plane, xy plane, so we take x equals a, let's say. So we take this region. When x is greater than a, we consider complex numbers in this region. Don't let it confuse you. If you get too confused, you can consider S as a real number. So instead of, if S is real, if S is a real number, the real part of S is just the number S itself. So if you become confused, you can, instead of real part of S, you can just put S itself. Consider it as a real number. Okay, now I continue with my examples. So example 2, Laplace transform of the exponential function itself, e to the a t. Here, a is a real number. Okay. Okay, you can, we may consider a as a complex number because we know how to, so if a is a complex number, say x plus iy, what is e to the at? E to the xt, oops, e to the xt plus iyt. So e to the xt times e to the I times yt, remember, is cosine of yt plus I times sine of yt. We already know this, so we can, instead of a real number a, we can consider a complex number a. It doesn't affect our computations. Okay, so what is the Laplace transform of e to the at? By definition, this is the improper integral from 0 to infinity of e to the minus st e to the at dt. So this is similar to what I did before. Minus, let me keep the minus sign, s minus a times t So this is the limit as m goes to infinity. If I integrate this, minus 1 over s minus a, e to the minus s minus a t, for t from 0 to m. So limit as m goes to infinity, minus 1 over s minus a, e to the minus s minus a times m minus e to the 0 is 1. Now, when, again, it's the same thing. The limit is 0 when the coefficient of m is negative, meaning s minus a is positive, so s greater than a. So this limit is going to be 1 over s minus a for s greater than a. If you consider s as a real number, when we consider s and a as real numbers. For s, a, complex numbers, it is still the same, the Laplace transform of e to the at, 1 over s minus a, but now the condition s greater than a becomes real part of s greater than real part of a. It is true that even if you consider s and a to be complex numbers, this limit is still 0 when the coefficient of m is negative. Because for the imaginary part y, you see the exponential function becomes cosine sine, and it is multiplied by the exponential function. You see it's multiplied by the exponential function where x is the real part of the number a. So cosine and sine are bounded functions. The limit of such a thing is going to be 0 when the limit of the exponential piece is 0, because cosine and sine are bounded. So it is enough to consider real parts. When real parts are negative, so real part of s is greater than real part of a, the limit of this exponential piece is going to be 0, and the Laplace transform of e to the at is the function 1 over s minus a. And here you can consider s and a to be real or complex. Okay, before we go any further, maybe using the linearity of the integrals, we can say the linearity of Laplace transform. So suppose Laplace transform of the function f is capital F of s for real part of s greater than real part of, or let's say for, let's take it for real numbers, and for complex, just replace it with the real part. For s greater than a, and Laplace transform of the function g is capital G for, say, s greater than number b. I'm not going to have enough space here, so let me go to the other page. Let me rewrite the lemma. So suppose Laplace transform of f of t is capital F of s for s greater than a, and Laplace transform of g of t is capital G of s for s greater than b. Then, when you take the Laplace transform of a linear combination, C1 f of t plus C2 g of t, it is going to be C1 capital F plus C2 capital G for s greater than, you take the larger of the two, maximum of AB. Whichever is larger, you take s greater than that one. Because I'm going to use this lemma, proof, I'm not going to give the proof because for the proof, all I'm going to say, the integral of C1f plus C2g is C1 integral f plus small C1 f plus C2g integral f plus C2 integral g. Because of the linearity of the integrals, you have linearity of the Laplace transform. So for example 3, I'm going to use this to find the Laplace transform of the cosine function. Okay. So to find the Laplace transform of the cosine function, I'm going to consider the previous example, Laplace transform of the exponential function, but now I'm going to consider the variable as a complex variable. So I'm going to write the cosine function using the exponential function of imaginary numbers. So of course, here A is a real number. A has to be real in order to do this. Okay, so if you consider e to the power I, the imaginary number I times AT, we know that this is cosine of AT plus I times sine of AT. And if you take e to the minus I times AT, this is cosine AT minus I times sine AT. So it's the complex conjugate, because if you take cosine of minus AT, it's the same as cosine of AT, and sine of minus AT is minus sine of AT. So we have the complex conjugate. So if you add the two, you get twice the cosine function. So you have, if you divide it by 2, add and divide by 2. So 1/2 of e to the IAT plus e to the minus IAT gives me the cosine function. So Laplace transform of the cosine function is going to be 1/2 Laplace transform of e to the IAT plus Laplace transform of e to the minus IAT. Now, by example 2, e to the IAT, the Laplace transform, is 1 over s minus I times a, right? Let me remind you, e to the AT, so coefficient a of t becomes s minus a on the Laplace transform. So here coefficient of t is I times a, so it becomes s minus I a, plus Laplace transform of minus IAT, so coefficient of t is minus I times a now, so s plus I times a. So if we get the common denominator, s plus I a plus s minus I a divided by s minus I a times s plus I a. So 1/2 2s divided by s squared minus I squared is minus 1, so this becomes plus 1 a squared. So if you cancel the 2, s over s squared plus a squared, and I need to take real part of s. Okay, so for which s is it true? Let's remember the condition. Okay, real part of s should be greater than real part of the coefficient of t. Coefficient of t is a. Now, so here real part of s greater than real part of IA. which is 0. I times A doesn't have a real part. So, so what is the result? Laplace transform of cosine AT is S over S squared plus A squared for real part of S positive. Of course, you can also use the definition of the Laplace transform to get this result. Then you need to integrate cosine times the exponential function. If you remember from calculus, you need to use integration by parts twice to get a circular argument and solve that circular argument to get the integral of cosine times the exponential function. But this is much more simple. Similarly, of course, we can also get Laplace transform of sine, because, okay, when you add e to the iat and e to the minus iat, you get the cosine. So if you look at the difference, you will get the sine function. So as the next example, Laplace transform of sine AT. So again, A is a real number. Now, okay, so now 1 over 2i times e to the iat minus e to the minus iat. If we go back, if you subtract, you get 2i times the sine function. So to get the sine function, we divide by 2i. So this is sine of AT. So Laplace transform of sine AT then is 1 over 2i times Laplace transform of e to the iat, 1 over s minus ia, minus 1 over s plus ia. So this is 1 over 2i, if you get the common denominator, s plus ia minus s minus ia divided by s minus ia, s plus ia. So 1 over 2i plus 2ia divided by s squared plus a squared. So we get a over s squared plus a squared. Again, this is for real part of s greater than real part of I times a, which is 0. So Laplace transform of sine AT is a over s squared plus a squared for real part of s positive. Okay. So this is example 4. Okay, now what about polynomials? Laplace transform, say t to the n. Let me call this f sub n of s. Okay, we are going to find a recursive formula for f sub n, and in this way we get here n can be 0, 1, 2, and so on. So for n equals 0, we already know the answer. For n equals 0, t to the 0 is constant 1. We know that this is 1 over s for s greater than 0. Right, this was our first example. Let's, yes, you see, from last time. Okay. Now for say n greater than or equal to 1, Laplace transform of t to the n, by definition, the integral 0 to infinity e to the minus st times t to the n dt. Now I'm going to apply integration by parts. I'm going to take u as t to the n and dv as e to the minus st dt. Then du is n times t to the n minus 1 dt, and v is minus 1 over s e to the minus st. So Laplace transform of t to the n. This is the limit as m goes to infinity. So u times v, minus 1 over s t to the n e to the minus st for t from 0 to m. And then minus integral from 0 to m of v du minus, so it becomes plus n over s t to the n minus 1 e to the minus st dt. Okay, let's keep going. Limit as m goes to infinity of the first part, minus 1 over s times m to the power n e to the minus sm minus, when you put t equals 0, it becomes 0. And then plus 1 over s times m goes to infinity, so the integral from 0 to infinity, e to the minus st, t to the n minus 1 dt. Now, this limit, this is the power of m compared with the exponential function. When in the exponential function, when the coefficient of m is negative, this limit is going to be 0. So the exponential is going to be in the denominator. And since the exponential function, you can use L'Hopital's rule n times or n plus 1 times whatever to get this limit to be 0. So this limit is 0 when the coefficient of m is negative. So this is when s is greater than 0. So 1 over s times, but this improper integral is the definition of the Laplace transform of t to the n minus 1, which I called f sub n minus 1. So what I get here is the recursive formula. F sub n is 1 over s times f sub n minus 1 for s greater than 0. Okay, we know that f sub 0 is 1 over s. So f sub 1, wait a minute, why 1 over s? I made a mistake. Okay, let me see. N over s, right? Yeah, here I have n over s. F sub 0, but this is for n greater than or equal to 1, remember. Okay, so f sub 1 is 1 over s times f sub 0. So this is 1 over s squared. F sub 2, 2 over s f sub 1, so 2 over s cubed. F sub 3 is 3 over s f sub 2, so 3 times 2 of s to the 4. So if you keep going like this, you get f sub n is n factorial over s to the power n plus 1. And this now we can take for every n because 0 factorial is 1. So Laplace transform of t to the n is n factorial over s to the n plus 1 for s greater than 0 and n greater than or equal to 0. Okay. Of course, for S complex, we have a real part of S greater than 0. I'm sorry, I should use complex numbers, but I slip sometimes, go back to real. Okay, now, what we are going to do next is generalize these two examples. Basically, how do we generalize? In the previous example, we computed the Laplace transform of the exponential function. How do we generalize this? In the next example, we will do Laplace transform of exponential function times some function. So exponential itself, you can consider exponential times 1. And now we take times any function. And how about this last one, t to the n? T to the n is obtained from, by the recursive formula, obtained from t to the n minus 1 by multiplying by t. So this we can generalize. How do we find Laplace transform of t times any function? Not t to the n minus 1, but any function. So this is the upcoming examples. But in order to keep things simple, short and simple, let's do this in part 3. So that's all for this video.